All right. Good afternoon, everyone. Thanks for joining, and welcome to the International Telescope Support Office, or ITSO for short, live at Keck event. We are located at the Australian Astronomical Observatory in Sydney, and we have here joining us two people from the Keck Observatory in Hawaii. All right.
Aloha. I'm Mark Cassis. I'm one of the support astronomers here at Keck Observatory. I'm in charge of one of our latest instruments, MOSFIRE, and together with myself and my colleague here, we spend about 30% of our time helping people from all over the world try to take the data and make the observations we want to do at night. And that includes our latest collaborators from Australia.
Hi, I'm Joshua Allender. I'm another one of the support astronomers here at Keck. I support mainly the high-res instrument, which is one of our longest-running instruments, and it's actually world famous because it's been involved in many of the planet discoveries that you've probably heard about.
Great. Thanks, guys. Thanks, Mark and John. Go ahead and set up. And we would definitely like to thank Keck Observatory for this great opportunity. There have been many great questions submitted by the public for this event. To help provide background for the science and the questions, I understand Keck Observatory has an introduction presentation to us, or sorry, for us. All right, and over to you, Keck.
All right, thanks, Elena. Yeah, so we've got a short presentation here just to give you a general introduction to the Keck Observatory and what we do. So one of the first big questions people often ask is, why do we do this? Why do we do astronomy? So there's a few reasons here. One is just general curiosity, and it seems to be part of the human condition. We're curious about finding the answers to questions like what are our origins? What is our fate? Are we alone in the universe? Obviously, a very fundamental question. And so this has been part of the human endeavor for as long as we've been around. This idea of exploration. The other thing we do is at Keck we work with the very most modern technology, especially in our instruments. So things like MOSFIRE, as Mark mentioned. We try to keep our telescope and the technology we're using right on the cutting edge so we can get the most out of the observations that we do. And a lot of this technology actually feeds back into the general public. So there's a lot of technologies that come out of astronomy that feed back into daily life. And then one other thing is that at Keck we take very seriously the idea of sharing our knowledge. So we do a lot of work here with the public, trying to do outreach, especially with the younger generation, to get them interested in science and technology, and to take on this quest for knowledge once we're done.
Let me just add that this job is actually fantastically fun as well.
Yes, it is. So, real quick introduction to where we are. So, we're located on the Big Island of Hawaii, and Hawaii is one of the most isolated land masses on the planet. So here's a quick Google Earth image.
And Josh, I think this image is actually upside down.
Actually, it's not, at least for some of our viewers. So Hawaii is located in the middle of the Pacific Ocean, and the nearest significant landmass is about 2,500 miles away from us. And this is actually important to what we do, but we'll come back to that in a second. So we're located on the Big Island, which is actually made up of 5 volcanoes. In fact, one of our volcanoes was in the news because fresh molten lava began flowing into the ocean in the wee hours of the morning. The Kilauea Volcano has been erupting for more than 30 years, and the eruption started flowing into the ocean again early this morning. So the Keck telescopes are located on one of the dormant volcanoes on the island, Mauna Kea. And the top of Mauna Kea is about 4,200 meters above sea level. And if you actually measure the height of Mauna Kea from its top all the way to the sea floor, where it emerges from the sea floor, it's actually taller than Mount Everest. It's just that the summit is actually lower down simply because the mountain is sitting on the sea floor rather than on the continental shelf. So you can see Mauna Kea marked there on the map. And then Mark and I are actually sitting right now at our headquarters in a town called Waimea on the northern part of the island on the Kohalas mountain range, one of the old volcanoes here. Here's a picture of the summit of Mauna Kea. And the two telescopes there in the middle, the two round white domes you see, are the Keck telescopes, Keck 1 and 2, that we'll be talking about. But Mauna Kea is home to about a dozen astronomical telescopes. So this is one of the forefront observatories in the entire world, and it's actually an international observatory. There are groups from all over the world who operate observatories here in Hawaii on Mauna Kea. Here's one more picture of Mauna Kea just at sunset. Yeah.
And this is one of my favorite photos of the mountain.
Yeah, so what's spectacular about this photo is you can see in the background the shadow of the mountain stretching out and being cast onto the sky behind the mountain. So I want to talk a little bit about why Mauna Kea is such a special place to do astronomy. You know, why did the telescopes come here? Why not anywhere else? And there's a few factors that make Mauna Kea really, really special. One is that, as I mentioned before, it's isolated. We're out in the middle of the Pacific Ocean. And one of the factors that astronomers like about Mauna Kea and similar sites is something we call seeing. So as light from the stars comes to us, it actually gets distorted by the Earth's atmosphere. The turbulence in the atmosphere actually distorts the image and essentially blurs it out. And because the airflow around Hawaii is so smooth, there's no mountain ranges nearby to disrupt the airflow, we get sharper images here than just about any place in the world, just naturally. So all of the telescopes on Mauna Kea benefit from this because they're simply sharper. You get better imagery here than they can almost any place else. Another factor that you can see in this photo is that because the elevation of Mauna Kea, again, we're about 4,200 meters, we're above most of the clouds here in Hawaii. So Hawaii is home to rainforests and lots of different climate zones, but the top of the mountain is essentially Arctic. It sticks up into this dry air above the cloud layer. And so as a result, we get more than 300 clear nights a year. So there's a lot of clear nights for observations. And then one last factor is that there's also very little artificial light pollution near here. The population of the Big Island is less than 200,000 people, so there aren't a lot of big cities nearby. So we get very, very dark skies. So altogether, we get some of the best conditions for astronomy anywhere in the world here on Mauna Kea. So here's a picture of, on the left, you can see one of our telescopes. And so what I wanted to emphasize with this slide is that Keck, the Keck telescope, the Keck Observatory, is quite an operation. We have a lot of people who work here during the day to make sure things run smoothly. We, in fact, run every night of the year, 365 nights a year. So there's no time, to shut the telescope down and do work on it for weeks on end. We have to get all the work we want to get done has to happen in between the nights during the day. So we have a day crew that goes up to the telescope and does all the maintenance and all the preparatory work for those night's observations. And you can see them at work in some of these slides.
And that upper right-hand photo is one of our staff on belay from the top of the telescope as he's trying to maintain something on the side.
So here's a picture of our day crew. And as you can see in this picture, we actually get snow here in Hawaii at the very top of the mountains. And so again, at 4,200 meters elevation, it gets cold enough that we get snow and ice in the winter. And because, again, we're dedicated to running every night of the year, one of the jobs that they do is they go out with snow shovels and clear snow and ice off of the dome after a snowstorm so that we can actually open that subsequent night. And so, yes, in Hawaii we get snow. In fact, the observatories own the only snowplow in Hawaii. So another thing about Keck is that Keck is the most scientifically productive telescope in the world. So this is a chart showing a bunch of the telescopes, some of the top telescopes in the world, and what you see in the chart is what's called impact. It's essentially a measure of the scientific productivity of the telescope. It has to do with how many papers get written based upon observations of the telescope, and are they actually cited, referred to by other scientists doing their work. So it's a measure of what is the impact of the observations that are happening at Keck on the world of science as a whole. And Keck is the world leader in this.
Josh, I just wanted to let you know that I contributed significantly to this by citing my own papers.
Well done.
Thank you.
So a few examples of some of this type of work. Here's one that you may be familiar with. The discovery of dark energy. So this was actually a Nobel Prize just a few years ago. And this group used observations from many telescopes, but Keck played a key role in a lot of these observations. And what they discovered is that the universe actually has a hidden component that we didn't know was there, that we're calling dark energy. And it's essentially a outward pressure. It's the energy density of empty space itself, pushing outward on the universe as it expands. And it turns out that dark energy makes up about 68% of the universe, so more than 2/3 of the universe as a whole. And it's sort of similar to this concept of dark matter, which you may have also heard of, which is actual matter of some sort, we don't quite know what it is yet, that makes up about 27% of the universe. And this discovery actually has Australian connection. That's Brian Schmidt, you may recognize in the upper right-hand corner there. Another piece of research done here over the last couple of decades is studying the supermassive black hole at the center of the Milky Way, our own galaxy. And what the observers did was they looked at the stars right down in the center of the galaxy over and over and over again. And they made a movie of the motions of those stars over time. And what they found, what you're seeing in these animations, is that the motions of those stars mapped out orbits. And these stars were orbiting something that wasn't visible in any of the images. But because we sort of understand gravity, we know how gravity works, we can measure how much mass must be there in that spot in order to make the stars orbit like this. And it turns out that you need a mass that's many millions of times the mass of our sun. And so this is evidence that there is a supermassive black hole at the center of our galaxy, because simply we don't know of anything that could weigh millions of times the mass of our sun without actually shining very, very brightly. It can't be a cluster of stars. It can't be a big gas cloud. And it has to be a black hole. And this was work led by Andrea Getz, who you can see there in the lower left corner. Another area of research is the search for planets around other stars. So this is something that Keck has been involved in for about 20 years now. And really what scientists, what astronomers are looking for here is we want to know, eventually, are we alone in the universe? And we think life exists on planets. And so we have to see how many planets are out there. What are those planets like? And so one of the things we're looking for is which of the planets are at sort of the right temperature, the right distance from their central star to have liquid water, for example. Because as far as we know, liquid water is required for life. And so we're looking for planets that are just that right distance, not too close to their star to be too hot where the water would boil off, and not too far from their star where they'd be too cold and the water would freeze out. And Keck has been involved in a lot of planet discoveries because we have an instrument I mentioned before called HiRes, which can very, very accurately measure the wobble of a star as it wobbles back and forth in response to the planet going around, and the tiny gravity of the planet tugging ever so slightly on that star. And then recently, Keck has been involved in direct imaging of these planets around other stars. Before we were just inferring their existence from the wobble, but recently we've used a technique called adaptive optics, which we'll talk about again later, to look at dim planets in very, very close to their host star. And what you see in this picture, that central blob in the middle is actually where the star is, and the star's light has been blocked out by something called a coronagraph, because the star is way brighter than the planets. And if you could see the star in this image, it would be so bright that it would wash out all these dim little planets around it. But sure enough, if we block out the star, we can see that there are these 4 little planets around that central star. And in fact, what we've been able to do is go back and re-image this planetary system and find out that all the planets are moving. And we can actually begin to trace out their orbits and prove that these are actually planets going around the star. These aren't chance faint stars in the background. And so Keck is involved in the very front line of research, things that are very, very exciting.
Josh, I think you got the wrong slide. This looks terrible. We didn't take this, did we?
Yes.
This can't be us.
We did, actually. So this is the planet Uranus. So we do quite a bit of planetary science here, looking at planets within our own solar system. And as I mentioned before, astronomers like areas in the world where there's good seeing, where the images are naturally very sharp. Well, Uranus is very tiny and very far away. So it's just not very big, and it looks kind of blurry. You can just sort of barely make out a few details in these images.
This is horrible. Do something about it.
Fortunately, we can. So one of the technologies that Keck employs is called adaptive optics. And with adaptive optics, we can actually measure the distorting effect of the atmosphere, and then using a tiny movable mirror, we can distort that mirror very, very rapidly and correct the blurring effect of the atmosphere.
Turn it on.
And the difference is dramatic.
Oh, thank goodness.
So these are the pictures once we turn on the adaptive optics. And all of a sudden you go from this blurry disk with just a few vague features, you can now see the cloud bands on the planet itself. You can see individual storms on the planet Uranus, and then of course you can see the thin ring system around the planet itself. So again, Keck tries to keep on the forefront of technology using things like adaptive optics. So that's our quick introduction to the Keck Observatory, and we're very, very proud to be here in Hawaii, and we really take pride in challenging ourselves to do things that are right at the forefront of both science and technology to get the most out of the observations that we do. Back to you, Elena.
All right, excellent presentation. This is really, really good introduction to give us a great idea of how this all works and what you guys are doing, and especially that adaptive optics. A lot of people are very curious about it because we've all seen great pictures like the one behind you on the wall with the laser shining out. Thanks for this wonderful introduction. And now we're going to get to the really, really fun part where we're going to start going through some of the questions that have been submitted over the last couple weeks on Twitter, on Facebook, and also through our website that we've been putting up. And I have a whole bunch of different questions for you guys. So I'm just going to put the camera onto you. And we're going to go through a couple different types of questions. And like I said, we've been taking questions for the last couple of weeks. So we had so many questions, we couldn't possibly answer them all. So we've picked the top 10. So those are the most requested questions. And then an example from that set. So this is the top 10 most requested. And all the questions will be put on our website afterwards with answers. But for this particular video, we're just going to be able to get to the top 10. So our first question actually comes from Twitter, and it goes all the way back to this wonderful telescope building that you have. And there's two buildings, like the one that's behind you now. So I'm glad the slideshow and the image behind you is keeping up here. So the question is, why do astronomers rotate the building? Is it just for fun?
Is it just for fun? No, it's not quite for fun, although because we enjoy our jobs, it is enjoyable to move the domes. But essentially, inside the domes, you've got the telescope, and the telescope has to point to different spots on the sky. And so in that picture behind me, the front of that will open up, and the telescope can look out of the dome. And then when we point to a new spot on the sky, the telescope will spin on the inside. In order to see out, the dome has to move with it. So the dome is actually on boxcar wheels that rotate, that help rotate it. And it sits there and it rotates very quietly at night and makes sure the telescope can see the sky. Now, sometimes we do use it for fun. During the daytime, when the dome is closed, we've taken people up there for tours. And it's kind of a Hollywood ride where we'll spin the telescope in one direction and spin the dome in the other direction. You can feel a little bit dizzy when you're doing that. But it's quite nice to see when you're moving the telescopes, and I encourage people to go up at sunset and watch all the telescopes move at the start of the night. It's really spectacular.
It's a great optical illusion when you're standing there and you get the impression that you're going the wrong way.
Yes.
All right. Yeah, I would say that it's definitely very, very fun. Now, keeping with the theme of the telescope, and we did get a lot of different questions about the telescope. Now, one of these sort of represented quite well, and it also comes from Twitter, which is how has working with a telescope changed from the days when Wilson and Hale scopes were the best in the world?
Well, actually, so first a little bit of background. The Wilson and Hale telescopes, these are 100-inch, 2.5-meter telescope at Mount Wilson in California, and the 200-inch, 5-meter Palomar telescope, also in California. And these two telescopes were each the largest in the world for a time. In fact, these two telescopes together were the largest in the world for most of the 20th century. And as you can imagine, things have changed quite a bit since then, especially the impact of computers on astronomy. So one of the first, most significant changes is that astronomers, well, first of all, we don't look through an eyepiece when we go to the telescope, and that hasn't been true for a very long time. But for much of the research that was done at Mount Wilson and Mount Palomar during their heyday, they used photographic plates as their detectors. They would take photographic film, it was actually on glass plates in this case, and the astronomer would expose a photograph of the night sky or of the spectrum output by their instrument. Today, we don't use photographic plates anymore. We use CCD detectors. These are just digital detectors, very similar to what's in commercial consumer cameras, in your phone camera, what have you. And so everything in the instrument is now computer controlled, and we get digital images up on the screen. In fact, in the old days, one of the key skills an astronomer had to have was darkroom skills. They had to know how to develop photographic plates. They would often do it at night at the telescope. Another big difference is that during the night at the telescopes at Mount Wilson and Palomar, the telescopes are first tracking the object as it rises and sets through potentially very, very long photographic exposures. And so the telescopes are doing the tracking, but no mechanical tracking system is perfect. And so the astronomer used to go up onto the telescope, literally riding on the telescope, and look through a little eyepiece on the side of the telescope which had a crosshair. And they'd center a star into that crosshair and then make tiny little nudges to the telescope motor to keep that star centered throughout this potentially hours-long exposure. The astronomer would actually be out there in the dome with the telescope doing this manual procedure of guiding. And of course today, again with digital cameras, we can have the computer do all that. And what that actually allows us to do is move the astronomer out of the dome, so they no longer have to sit in the cold.
So much better.
But the other thing that we are doing here at Keck is that we can now do remote observations. So the astronomer doesn't physically have to come to the observatory anymore. So we actually, for any of our new users, they actually come out here to Hawaii and visit us, and we train them how to use the telescope. But subsequently, they can observe remotely from computer stations. And we've got, what, about 10 or 15 of these set up around the world. And they're set up basically to match our control station here in Waimea. And the astronomer can sit there. They can see the same control screens on their computers that we see here. And they can work via a teleconferencing system with the observing assistant. This is a Keck staff person who actually operates the telescope. They'll actually steer the telescope, point the telescope, and they're responsible for sort of safety of the equipment. And the astronomer can focus just on making sure that they're getting the data they need for their science. They'll be running the instrument, controlling the exposure. But now they can do this remotely without traveling to, again, a very isolated landmass here in the middle of the Pacific. So those are the major differences between observing at Palomar and here.
Great, yeah, and that's a very, very popular method, especially for those of us here in Australia. We're also quite far away from anywhere else, and so to get from our faraway location to your faraway location sometimes is a little bit too much, and we have 2 remote observing stations with Keck at the moment, one in Swinburne and one at the ANU. So if you're more interested in that, make sure to check out the websites. And yeah, it's really wonderful. It's the same technology really that we're using now to do this live stream. So moving on.
Although we like to take advantage of those facilities, I will say that Josh and I also like seeing you here at Keck. it's much more fun to hang out here at night rather than over a polycom.
Yeah. One of the nice things about this job that Mark and I do is we get to meet all of these astronomers who are coming literally from around the world to observe with Keck. So we actually get to talk to a lot of different people doing a lot of amazing science.
Oh yes, I completely agree that being at the telescope is much more fun. But it does allow those of us who can't get there to do it, the observing, so it's a compromise, I suppose. So the telescope questions were quite a few. We also had some questions about what Keck looks at and what type of light Keck looks at. In particular, also coming from Twitter, what wavelengths does Keck observe at? So can you address a little bit what types of light that Keck uses or looks at?
Yeah. So Keck is an optical and infrared telescope. It actually can operate from about, if we're going to be technical, it goes from around 3,000 angstroms to basically 2.5 to 5 microns, depending on the instrument that we're using. So we have 8 different instruments. Half of them are basically designated to observe at wavelengths that your eye can typically see, so the optical wavelengths, and the other half are designated to be able to see what your eye is just off into the infrared, from about 1 to 5 microns. So all those instruments get scheduled depending on the moon phase for the most part. The infrared instruments go on when it's a full moon, and the optical instruments get put on when it's a full moon. Sorry, new moon. Thank you, Josh. And a few of those instruments are very specifically designed to look at UV radiation. So LRES, which is a multi-object infrared spectrograph. ESI is a single object IFU spectrograph that's designed to get down to the very edges of the atmospheric cutoff for the UV bands. And then some of the other instruments at the other end of the extreme, we've got NIRSpec and NIRC2. NIRC2 is one of our AO instruments, and they can see out to what we consider the thermal bands at around 4 and 5 microns. So between those instruments, we've got a set. They're all different and very unique, and the observers use them in very unique ways depending on what their science cases are. Hope that answered your question.
Yeah, that's and you know, one thing that's very interesting about the different wavelengths is they actually show different things. Now, I know some of us might still be old enough to remember the old Predator movies, and the common analogy,
Yes.
infrared, you get your Predator vision, so you're actually seeing. So you're actually seeing a bit of a different thing. Now, what about ultraviolet light?
The ultraviolet light, you know, that's just off the edge of where your eye can detect in the blue. That's the kind of stuff that you got to worry about in terms of, especially in Hawaii. We put on a little thing called sunscreen to help protect our skin out here.
Exactly, and we worry about that a lot here in Australia because of the problem with ultraviolet light here.
So it turns out ultraviolet light is actually absorbed by the Earth's atmosphere. And there's a lot of interesting things that happen in the ultraviolet that we just can't see. But because Mauna Kea is sort of up in elevation, more of it gets through up on Mauna Kea than in most other places. So we have a few instruments that are designed to work as best they can into the ultraviolet. So LRES and HIRES are 2 of our optical spectrographs. And in fact, HIRES has a special mode. We have a second set of optics that we put into the system for some science that really wants the best possible performance down at that what we call the UV cutoff.
Right. So, and it's you know, the Keck Observatory is basically better than Predator because it can even see in even more than infrared. We've got UV, optical across the board. So very, very great telescope. Now we have another question which was submitted on the website, and we actually, it looks like we have the submitter in the chat with us.
Oh, that's cool.
Yeah, so we, the question was that could we please explain why a powerful laser beam is used to track the stars? And it was submitted by Abhijan Dutta, who I believe is here with us in the chat. His audio is not on at the moment, but hello, thank you for submitting your question onto the site. And if you could please go ahead and... Talk about the laser beam.
Okay. So the laser beam is related to the adaptive optics system that we mentioned before. So just a quick background. Adaptive optics, what we're doing there is we're trying to, again, correct this blurring effect of the atmosphere. So in order to do that, we have to, first of all, measure that effect. So typically what we do is, we find a really bright star next to whatever it is we want to observe. And then by looking at the light from that bright star, we can essentially measure that blurring, because we know the star is supposed to be a perfect point, we can see it's kind of blurred out, and we have some instruments that can actually measure what we call the wavefront that's coming through. And that wavefront is distorted. So what we do is inside the instrument, we bounce the light off of a little tiny mirror, just a few inches across, and that mirror has lots of little actuators on the back that we can move very, very quickly. So we can essentially change the shape of this mirror to de-distort the images as they come in from the telescope. And you can imagine we have to do this very, very quickly because the atmosphere is constantly changing. So we can actually update the shape of this mirror roughly 1,000 times a second. And that's what we have to do in order to sharpen up those images. But of course, if you're taking images 1,000 times a second, you've got very, very short exposure times. So again, you need a really, really bright star in order to do adaptive optics. And unfortunately, there just aren't that many bright stars scattered around the sky for us. So what we needed was a solution that allowed us to measure the distorting effect of the atmosphere. Well, it turns out that we're actually kind of lucky, because very high in the atmosphere, about 100 kilometers up, there's a layer of sodium atoms. And those atoms are actually deposited by meteorites burning up in our atmosphere. And what we can do is by taking a laser, a powerful laser, and shining it up, and if we tune the wavelength of that laser just right, we can excite those sodium atoms. We can, give them energy, which causes them to glow. And then we have a little tiny glowing spot at the very top of the atmosphere, and that's an artificial star. And we can then use that artificial star to do this measurement of the wavefront error. So we can figure out what the corrections need to be applied to the dim thing that we want to observe nearby. And again, with the laser, we can steer that anywhere in the sky, and we can suddenly do adaptive optics anywhere we want to, rather than being limited to this tiny, tiny fraction of the sky that was really close to a bright star. So that's why we use the laser, and it's always used in concert with one of our adaptive optics systems.
And right behind it, there's a laser.
Perfect timing. And we use the adaptive optics system about how often would you say?
It's about 25 to 30% of the time. Yeah. It's about 60 nights a semester, so 120 nights a year. That's between the two telescopes. So we got a laser on Keck 1 and a laser on Keck 2, and both of them use different instruments behind them. And those instruments do different things.
Yeah, so this adaptive optics system essentially enhances other instruments.
Great, and that's what we saw earlier in your slideshow when you showed the beautiful pictures of Uranus once they've been enhanced. Excellent. All right, so thanks very much for submitting that question, and I'm really pleased that we also had the person join in, so great. Hopefully that answers what was going on, and if not, you can always find us later on Twitter with #ITSOAO or on the website. All right, the next question was also submitted by Evan, and this question is, can members of the public request a specific celestial object be targeted, and if so, what are the requirements to make a request? So this goes under all the questions that were asked about how do the observing request
get time, huh? So Keck has different institutions have their own time allocation committee, and so in order to get time on Keck, you usually have to go through one of these groups within your own institution. So we've got Caltech as a partner, the University of California system as a partner. Australia has their own TAC, or time allocation committee. So I usually say it's very difficult for an individual to get time on Keck. However, at least within the U.S. community, anyone can propose to use Keck as long as they propose through the NASA time allocation and proposal process. So usually what happens is I want to use a telescope. I make a clear scientific case. I propose that scientific case to a peer-reviewed panel, and they judge my science. And if they judge it worthy enough, then the TAC will approve my observations, and then that'll go through a scheduling process through someone here at Keck, who then tries to figure out what day I can actually, what night I should say, what night we can use, or what part of a night I can use. And then that comes back to me, and I'm able to fly out here or use one of the remote facilities to take that time. So I'm not sure how it works in Australia, but at least in the U.S., it is possible for anybody to get time on Keck as long as they can justify, very scientifically, the reasons for why they want to look at their astronomical object. It's not very often that you can just propose to say, I want to look at Jupiter and snap a picture.
Unless maybe you're the director.
Unless you were the director.
There's some advantages to being director. Yeah, and it's actually, Keck is in very, very high demand. So all of our member TACs typically get many, many more requests for nights than there are nights in a year. And so we are heavily oversubscribed, is what we call it. So there's a lot of competition to get nights on the telescope. So when an astronomer gets assigned a night on the telescope, that's, quite precious. Those nights are very, very special.
Coming out of NASA, I think that oversubscription is somewhere in the neighborhood of like 1 to 6 or 1 to 10. So it's kind of tough.
Yes, and I will say that if you are in Australia, it is a little bit more limited than if you're going through the US. So if you're in Australia looking to get time, there's many fewer nights available that you can actually apply for. I believe right now we only have 45 nights over all Australia, and I know Swinburne has their nights and ANU has their nights, and it's all bundled into one big KTAC. So it's also quite competitive.
Yeah, very collaborative.
Yes, very collaborative. So again, we do have it a little bit different here as well. Great. Okay. So let's moving on. We've also got a great question that I had not thought of, but it does seem like now that I think about it, there are many different answers to this question submitted by Matt. And that is, how do the people that work the telescope get their food?
That's actually kind of an important question.
I love it.
So first of all, there's a lot of different people that work there at Keck. We have a staff of well over 100 people to run both telescopes. And we actually have different crews within that. And so Mark and I, we do most of our work here from the base facility in Waimea by the headquarters, along with a lot of the engineers. We also have a set of employees that we call the day crew, and they actually go up to the telescope every day to do maintenance, make sure everything's ready for the night, do any instrument changes that might need to be done. And then we have our night crews who are actually at the telescope every night, executing observations in concert with the astronomer who may or may not be remote. So it varies a little bit for each one of those. So for the night crew, which is probably the most interesting, our observing assistants actually operate the telescope, and about half, well, a little more than half of the time, they're actually physically at the telescope, in the control room at 4,200 meters elevation on Mauna Kea. And they'll go up for shifts several nights at a time. So they'll be up there 3 to 5 nights. And so rather than commuting back and forth every day, we get very long, obviously. There is a mid-level facility called Kilauea, and that's at about 2,700 meters elevation. And all the observatories on Mauna Kea collaborate to run that, and it's basically a dormitory and cafeteria. So the OAs can actually stay the nights, or well, stay the days in their case, they sleep during the day, at the dormitories there at Kilauea, and then at the cafeteria they can get their meals before they go off, after they come down, and then they can take up their essentially night lunches, because their lunch is in, of course, in the middle of the night. So that's how the night crew get their food. And then our day crew, because they're up there all day, they'll commute each day from the lower levels, because they're often taking equipment and whatnot. They actually also stop at Kilauea because the dramatic change in elevation from sea level 4,200 meters, it's actually recommended that you acclimatize for a while. So they stop for a minimum of half an hour at this mid-level facility to get used to the altitude. And so they'll actually take a meal at Kilauea on their way into work in the morning as well. And then for those of us fortunate to work remotely from Waimea, we've got restaurants and grocery stores within walking distance that are actually quite fantastic.
Korean barbecue, Thai food. Those are my favorites.
Excellent. Yes. Well, and I know that a lot of us who've worked at telescopes have interesting adventure stories about times we may or may not have forgotten to bring food with us.
Your body, when you're up there, you really need something to eat. Your body is going through a significant metabolism rate. You can get cold quickly if you're not eating something.
Yes, and that is actually a lot of us are very familiar with bringing lots and lots of snacks. So it's a justifiable expense during observing. You must have snacks. So great. And this is a great question, too. The food of astronomers is something, yes. All right, so now going back a bit into more of the astronomy side of it, and what Keck can look at, we had an anonymously submitted question on the website, which is still quite good, and a lot of people were asking about how far or what distance Keck could look to. So the question I'm going to give is, what is the farthest object observed or observable by Keck?
Okay, the farthest, Keck itself kind of holds, as far as I know, it holds the redshift records from the ground. Both Deimos and Mossfire, so those are both optical, and Deimos is an optical spectrograph, Mossfire is an infrared spectrograph. Between the two of those, they've been looking at objects at the very edges of the universe. So, just after the Big Bang, there's a bunch of hydrogen soup. Eventually, stars and galaxies started to form inside that soup, and it's now Mossfire and Deimos, along with Keck, are trying to push the observational faintness limit to see these things kind of inside that, just as they were forming, and trying to find them at a very early age. So redshift record, I think, is about 8.6. That translates to about 13.2 to 0.3 billion years back in time. When we talk about distances in the universe, when you're looking at things that far out in the universe, we think of them in terms of light years. So it's it's 13.2 billion light years, and we actually have to think about how fast light travels in that time in order to figure out an actual distance. So Keck has been doing a lot of work right now trying to understand objects out of that, what types of objects that they are. Are they really big galaxies? Are they a collection of small galaxies that are starting to basically reionize hydrogen and helium out of those distances? And so, where was I going with this? Keck has been really a leader in trying to find the most distant galaxies out there. And since Mossfire has gone on the telescope, it's about every 6 months we get a new push further and further out to see how far we can see. It's really exciting. Often an observer will be, I'd say like once a month, an observer will bring either Josh or myself over and tell us, hey, look at this. They've never seen anything like this before. And at least right now with Mossfire, it's often a redshift that they haven't seen before. It's really cool, really exciting.
Yeah. And exactly, and a lot of us here in Australia will have recognized Brian Schmidt from your slideshow and the redshifts that he and his group obtained. So that's part of their Nobel Prize winning discovery. So I'm sure many Keck observations were used.
Yes. Oh, yes. Especially that a lot of those observations were made with the multi-object spectrograph LRES in mapping out the universe and seeing those things. So
Great.
It's all perlmutter not to look like that picture anymore.
And once again, we have our Australia connection. All right. Let's see. We also had another anonymous submitted question, which actually goes right to the meaning. Why is it called Keck? And by it, I mean you, the telescope. Why is it called Keck?
Yeah. So to answer that, I'll give you a little bit of the history of the telescopes here. So we talked about the Palomar telescope earlier, and for a long time, Palomar was the largest telescope in the world. It had a mirror that was 5 meters in diameter. And of course, the bigger the mirror, the more collecting area, the fainter you can see. So this has always been a push for astronomers. And in the 80s, some astronomers at the University of California system were trying to figure out how can you build a bigger telescope. And the trouble was, the telescope mirror in Palomar is made out of a single piece of glass, 5 meters across, and then you put a thin coating of aluminum on it to make it reflective. The trouble is that glass isn't very stiff. You can shape it very, very precisely, like you need to in order to make a telescope mirror, but it tends to warp under its own weight, and making the glass blank for the Palomar mirror was very, very difficult. And basically, we can't really make 10-meter mirrors out of a single piece of glass. And the idea that they had was to, rather than try and make a telescope mirror out of a single piece, let's make it up out of a bunch of smaller pieces and tile them together like a mosaic. The big challenge there is that you have to take each of these pieces and get them, edged up against one another, and then get the positioning just right, and then the tilt just right, so they act as a single uniform piece. And this was technology that had really never been done before. And so this group worked in the lab and built prototypes. They were proving that they could do this, and they wanted to build a large telescope. And of course, the challenge with a large telescope is you need a lot of money. And what ended up happening is that the telescope was initially built, a partnership between the University of California and Caltech, and the money to build Keck 1 was donated by the W.M. Keck Foundation. That's where the name comes from. And W.M. Keck Foundation was actually founded by W.M. Keck, who was founded Standard Oil in the 1920s. And so he became very, very rich. And when he died, he created this foundation for the advancement of science, among other things. And so there's actually quite a few things around the world named after Keck. We happen to be the Keck Observatory, but you can actually find there's another Keck telescope. There's many, many Keck schools of fill in the blank. So this charitable foundation actually funds quite a bit of scientific research. And so that was the origin story for the Keck telescope and the name.
I'll also add that Keck itself is a 10-meter telescope. The other telescopes that have come online are smaller on the mountain. They're only 8 meters. And it was this technology that really appealed to Keck, and he thought that this was something that he was willing to back and put his money behind, because it was such a cool and unique technology that he felt like this was a bust or boom, I guess, in some sense. And so he was very excited about it. It was also at a time when computers were coming online, and so there's a real controversy as to whether a computer had the ability to solve the mathematical functions to come up with the right curvatures as well as correction algorithms to keep all these mirrors in the right alignment. So that uniqueness really appealed to Keck at that time.
Yeah, and in fact, Keck was very much right. All of the large telescopes from here on out, anything 10 meters and up, will be built with some variation on this technology of tying together multiple independent mirrors and using the computer control to get them to what we call phase up, so they act as one giant mirror. This is the way that the technology is going.
And we think that W.M. Keck was actually superior oil instead of Standard Oil.
Oh, I'm sorry.
All right, great answer. And yeah, it is very interesting about how the history of these things come about. Now, we have a more technical question, because a few people were asking how do the telescopes work, or why are there two? And so the sort of example question for that sort of category comes from Mary, and she asks, does having two telescopes give the Keck Observatory depth perception? And how does that help the images received? So why are there two?
Why are there two? The reason why there are two reasons, I think, behind why there are two. One is that they were thinking about, Keck 1 was very successful and they wanted to make a copy of it, and so they moved forward with that. The second is that they wanted to use them in tandem, and we did use them in tandem for a little bit using a technology called interferometry, and that allowed us to see things in more detail, or better enable us to resolve the stuff out in the universe to finer and finer detail based on how far apart they are. So the size of the telescope matters in terms of your resolving power, and if you can put two telescopes far apart and use them in tandem pointing at the same spot on the sky, then you can use that baseline from one spot to the next spot to help you in terms of resolving things. Now, two telescopes themselves just put farther and further apart does not make a big telescope. The light gathering power is not as big as something that was all-encompassing, the same diameter. So it turned out that Keck itself became a lot more scientifically productive to use them as individual telescopes. So we started using, especially with adaptive optics coming online on Keck 2, we started using this telescope predominantly for adaptive optics and left Keck 1 at the start just a limited telescope. But eventually put an adaptive optics system on Keck 1 as well. And so although the telescopes themselves don't get used in simultaneously to look at the same object and combine that data between the two, we do sometimes have observers who will use the two telescopes simultaneously to study different aspects of the same object. So Keck 1 will be using one particular instrument with its adaptive optics system, and Keck 2 will be using another instrument with its adaptive optics system. And they'll be studying two different aspects of the same object to understand it in more detail.
Great, so more information, which is always good. And interferometry, so just to make it the distinction, by gaining in resolution, what exactly are you gaining?
You're gaining your ability to see certain details. So instead of reading the date on a quarter at arm's length, you might be able to read it across the edge of to the other side of a building with interferometry. But
and it's not depth perception, but it is still very useful in some cases. I believe I recall that Keck used this at some point with the Galactic Center, didn't it?
It did.
Yes.
For a brief while, we were looking at the Galactic Center. We were also trying to use the system to look at very bright stars, so the interferometry was kind of limited to much brighter objects in the universe. And so we were using it to understand planetary disks around some very young stars and trying to resolve the positions of the disks and what was in the disk at the time, what kind of dust or gas was in it.
Great. So that, yeah, very fun question. Okay, so for our last representative question, this is last but certainly not least, we have a question that actually came from Brendan O'Brien from Astrophiz Podcasts. And he asks, will Keck and James Webb Space Telescope team up for joint research projects? And is interferometry a possibility? So also asking about interferometry.
So the short answer is very much yes. So again, I'll go back and talk a little bit about the history of Keck. Keck 1 came online, saw first light in 1993, and Keck 2 just a few years later in 1996. And that coincided with the Hubble Space Telescope. And it turns out that this was a fantastic partnership. So observations with Keck and the Hubble Space Telescope were used together very frequently. And it was a great collaboration because the Hubble Space Telescope, it's in orbit around the Earth, and it doesn't suffer from that blurring of the atmosphere that Keck does. And it can also see into the ultraviolet, where our atmosphere again blocks those ultraviolet, the light from getting to us. But the Hubble Space Telescope is still a relatively small telescope. Its mirror is 2.4 meters in diameter. So it's very similar to that Mount Wilson telescope in size that we talked about earlier. And the Mount Wilson telescope was built in 1917, so it was very, very old. But the advantage was that, so for example, you might be familiar with the Hubble Deep Field, where they looked at one particular patch of sky for a very long time, and they were able to look very, very far back in the universe. And so they would see, you know, many of these distant, faint galaxies, but they were just the tiniest smudge on the image that was a very, very long exposure. And in part, that was because Hubble is a relatively small telescope, doesn't gather as much light. When they find distant things like that with Hubble, Keck is large enough, it has enough collecting area, it gathers more photons, that they could actually study those things that they discovered with Hubble in much more detail with Keck because of the additional collecting power. So that was the collaboration through basically the 90s and 2000s. And the James Webb Space Telescope, JWST, is essentially the successor to Hubble. So JWST, rather than being 2.4 meters like Hubble, is 6.5 meters. It actually goes a little bit more into the infrared, so it doesn't do optical and ultraviolet, but it pushes towards the infrared. And interestingly, the James Webb Space Telescope is not a monolithic mirror. It's a tiled group of hexagonal mirrors, the same technology that...
where they got that idea.
Exactly. So it's the same technology that was developed here at Keck in order to build large mirrors. And they did that because they simply can't put a big 6.5 meter diameter mirror into a rocket. It's just too big. But if they fold it up, they can pack it into the rocket and then unfold it once they get into space. So James Webb, which is expected to launch in late 2018, is the next generation of space telescope. And we fully expect there to be a lot of collaboration between Keck observations and JWST observations. Because again, Keck is still a larger telescope. It's much, much easier and cheaper to build large telescopes on the ground than in orbit. And Keck, now that it has adaptive optics, can do great work in near-infrared and visible light. It's got the resolution that James Webb doesn't, because James Webb focuses on doing those sort of 2 to 5 to 10 micron wavelengths that we mentioned earlier. So we expect a lot of good scientific collaborations between the two telescopes. And then the second part of the question was about interferometry. And unfortunately, the short answer for that is no, we're not going to be able to do interferometry. So interferometry, again, is this technique where you can take multiple telescopes and combine their light in a way to get the resolution information of a much, much bigger telescope. It's a technique that's been used in radio astronomy for a very long time. And unfortunately, it's very, very difficult to do at optical and infrared wavelengths because the wavelengths of light, optical and infrared, are very tiny. They're half a micron, things like this, whereas in the radio, they're millimeters and even centimeters. And that basically, that wavelength tells you how accurate everything needs to be built. And the trouble is that in order to combine the light from JWST and Keck, you would actually have to beam the light from JWST down through the atmosphere to Keck, and the atmosphere again blurs things out. So it would be, with our current technology, it is essentially impossible to do this sort of interferometry between two telescopes that are so distantly separated. Maybe many, many years in the future, and especially if you had two space-based telescopes, but doing interferometry between an orbiting telescope and one on the ground is essentially impossible with current technology, unfortunately.
Right, yeah, and space-based interferometry has been proposed, as have, I believe, space elevators, but we're a bit far away, I think, from either one of those solutions. All right. Okay, well, great. That was our last question. So that's sort of the end of the Q&A, and like I said, we will put all of the questions up. But it's always great to hear from Keck Observatory, and I'm really glad that Australia and Keck are building such a great relationship. This has been super fun. Do you guys have any final thoughts?
It's really nice to see people from Australia coming and visiting Keck Observatory and having great interactions with them and learning about the science that you do. I'm looking forward to visiting there, hopefully, and hanging out and having a beer. So hopefully we'll make that happen.
Yeah, I'm really looking forward to working with more and more astronomers from Australia. I have actually had the opportunity to visit some years ago and learned to appreciate Australian rules football during my observer run. So yeah, it was a lot of fun. I look forward to seeing more folks from Australia here at Keck.
So thanks for your questions. Say aloha, as we say here in Hawaii. So thank you very much.
Yeah, thank you.
All right, great. Okay, remember this video and all the questions asked and their answers will be hosted on our website. That's https://www.aao.gov.au/ITSO/outreach/KeckLive2016. So thanks to Keck and Keck Observatory and the AAO for making this possible. You can find the ITSO office every week on Twitter with the hashtag ITSOAAO, as well as on our website, which is the AAO/ITSO website. All right, thanks everybody.